So, as Sheila, my chairperson, was saying, I'm Valeria de Paiva, and I want to talk to you about modal type theory today. But of course I want to, given that I was given this honor of opening this wonderful meeting, such a big and interesting meeting in Natal, I want to start by thanking the organizers, particularly Elaine and João Marcos, but then everyone else too, for the invitation. It's just lovely to be here. And Mario, and kind of lots of people who kind of made this thing work for so many LFSA kind of work for such a long time. I'm very partial to this conference. I think it's a great thing that people have been doing for a while now in Brazil. So, and you know, I've always paid to come here to FSA. This is the first time that I've been invited, so I'm kind of feeling kind of happy, over happy to be here. And I want to talk to you about modal logic. And modal logic is something that there's lots of people in the audience that are know much more about it than I do. And it's not one of my specialities, but it never stopped me before, so it won't stop me from talking about it now. And I wanted to start exactly with a quote from Lord Russell, that there is no fundamental logical notion of necessity, nor consequently of possibility. If this conclusion is valid, then the subject of modality ought to be banished from logic, since propositions are simply true or false. It's kind of hard, isn't it? It's heavy. He's not one of our friends at the moment. But actually, I only kind of heard about the quote on the very long paper of Rob Goldblatt about the history of mathematical modal logic. So I think it's okay. No one paid much attention to Russell on this one. So I'd rather use this quote. And as I was saying to Sheila minutes ago, I actually gave this talk in a very August place. I gave a colloquium in Berkeley, and I had two of the biggest luminaries of many very important people, but I had Dana Scott and Martin Davis, and even Craig interpolation theorem sitting in the audience. So, as I was saying, it never stopped me from babbling on things that I don't know enough about. But I kind of liked this quote from Scott. The paper is called Advice on Modal Logic, and he says, one often hears that modal or some other logic is pointless because it can be translated into some simpler language in first order way. Take no notice of such arguments. There is no weight to the claim that the original system must therefore be replaced by the new one. What's essential is to single out important concepts and to investigate their properties. And that's what I want to do in the next 40 minutes, if we can. The only kind of funny thing that happened is that this is Dana Scott in 1971. It's, I had a picture of him looking much older and with Grisham, and he complained. He sent a message saying, no, this is not correct. And I said, what, did you change your mind? Don't you think that's quote? No, it's not that. It's just my picture. My picture, I was much younger when I said this. So I'm siding with Scott, and I'm sorry about the slides put here in the last night. Today I want to do two things. I want to discuss with you a bit on constructive modal logic's challenges and opportunities, and then I want to show you an easy is in heavily marked quotes, because it's easy for some people, but not for everyone. It's an easy dependent system. And the thing about it is that I thought an invited talk needs to be more, I wanted just to talk to you about my new toy, this easy dependent system. But then I thought, it's not nice. You kind of go all the way from California to Natal to talk to people about things. You have to kind of give something that's more general, more exciting, more interesting than just a specific new thing that I've been playing with recently. But I wanted to show you something slightly different too. So let's see how it goes. So some people here are also involved with me on this program of doing intuitionistic modal logics. And this is a kind of very interesting program because, you know, we never had any money from anyone. And we have been doing that for a long time. And the idea here is that modal logicians, philosophical modal logicians, have lots to say to the guys in type systems and in kind of principles of programming language, kind of in functional programming languages and type systems. They have lots in common. They actually sometimes study exactly the same thing, but they have different tools, different mindsets, and they sometimes don't realize they are talking about the same thing. So the whole point of this collection of researchers that I call intuitionistic modal logic and applications, the IMLA is the acronym. The whole point of it was this idea that there is a hope that we could get philosophers, mathematical logicians, and computer science exchanging tools, exchanging information, exchanging ideas. And that the only point was that they did not know that they were doing similar things, and hence we wanted to kind of have them in the same place. And this has worked very well so far. So we had, I mean, to a certain extent, it has worked. We've had 6 big workshops, normally associated with LIX or Flock and stuff like that. And you also had several special volumes, and the last 2, you see that, you know, Elaine being the very organized person that she is, she managed to overtake the one from 2001 only appeared in 2015, but the one from 2013 appeared just after the meeting itself. So it's kind of, and these things appeared in reasonable places. So I think there was, at least for a long time, a feeling that this idea of constructive modal logics was worth pursuing, was an interesting subject of research and useful for different people. So what do I mean by intuitionistic modal logic? The basic idea is totally easy, right? What I want to have is modalities over an intuitionistic basis. And why I want that? Well, because I think the modalities are very useful, particularly in computer science, where you have different phenomena that you want to model. And why an intuitionistic basis? Well, because as I was saying a minute ago, we want to engage and do work with people doing principles of programming language, kind of verification of compilers, and all this kind of work on type systems that you know, in some ways go back to Russell, but in some other ways are kind of things that we have been doing since the 1980s with all the work of Martin Löf and the guys who kind of, and Scott and Strachey and people who kind of started thinking about programming as kind of logic in disguise, the people who kind of put in place the Curry-Howard isomorphism. But if you decided that you like this idea of modalities over an intuitionistic basis, then you have a collection of things that you have to answer. So you have to decide which modalities you want to discuss, which intuitionistic basis you think is best for you, why, how, which proof systems, why there are so many, because soon enough you realize that there are loads of them, how to choose between the many. That's okay. It's not me. It's not my telephone. It's good. So how to choose, how we can relate one system to the other, which are the important theorems, and which are the most useful applications.
Sorry to forget.
That's okay. It's moving. Cool. Okay. So, and some people that I talk to kind of would say, well, you know, why did you say modalities are important? Why do you think that these things are worth thinking about? I mean, Russell himself was saying, no, they are not, right? But we think that modalities are, I think modalities are the most successful logical framework in computer science altogether. There's things like temporal logic, knowledge operators, BDI models, the notation semantics, and logic is used particularly modal logics are used both to create representations and to reason with the representations. So these two sides of modal logic are important and different. But usually, when people say that modal logic is the most important logical system in use, they mean classical modalities. So I think in previous versions of this talk, I talked about the number of citations of modal logic and stuff like that, trying to use Google as a proxy for importance in the field. But now I kind of decide to use Frank Fanning's proof by authority. So I'm trying to use Frank Fanning as a way of saying how important modal logics are. So Frank decided to go for the awards, right? So, the ACM Turing Awards in reasoning about concurrency, reasoning about hardware, model checking, temporal logics, branching time, and CTL, and all this, and all the knowledge representation. He kind of chose these guys that I hope the people here kind of have heard of and have been exposed at least a little to say that modal logics really are essential. So even if Lord Russell doesn't like them, we should pay attention to them. And as I was saying, my basic point is that intuitionistic modal logic is not that used, and there are several different takes on the notions of intuitionistic modal logic, and my take will be very much from the point of view of Curry-Howard correspondence. So trying to think about principles of programming language, trying to think about Curry-Howard as my important, my guiding light. And then I want to try to kind of have at least a go at some of those questions with you guys. And please feel free to interrupt or ask questions or say things if you feel like it. Now, I hope in this audience I don't need to belabor this point, but in several places that I talk to, I have to say why I think constructivity is important. And my constructivity is not philosophically very informed, it's very pragmatic, so I say that I personally prefer that if you ask me if there is an X such that P of X, I much prefer an answer like, yes, that's my X, that satisfies P of X, than the answer that there is an X, yes, for all X, it's not the case that not PX. Because I'm very simple-minded. I do not like these things about for all X. There is not one X. It kind of gets me confused. I like to have things constructive, and lots of classical mathematicians and people who kind of think classically but are computer science also like that idea. So what I want is reasoning as precise and safe as possible, and I will try to be constructive as much as I can, but a proof is a proof. It's better than no proof, and if I need to be classical, so be it. And I want to kind of I want to try to reinforce this idea that constructive modalities ought to be twice as useful as the classical modalities that we saw in the slide that just passed, the one about getting lots of Turing awards and big systems that are used by industry and stuff. But I have to say that my evidence here is not as good as I would like it to be. And one of the reasons for that, I think, is this business that constructivizing things is always prone to the problem of multiplication of frameworks. It's something that we know about constructive mathematics, and it happens in the constructivization of logics in general, that whenever you try to constructivize a notion, you have several different possibilities, and then you have to choose between them. So the constructive notions of anything, any X, multiply themselves. So what do I mean by Curry-Howard correspondence? And if you don't know already, you're not going to get a very good grasp just by listening to these two second description. But at least you have pictures, so you might remember them by the pictures. So for me, Curry-Howard correspondence will connect not only lambda calculus in several different possibilities, and I have lambda calculus represented by Church, not Curry, of Curry-Howard, but Church, and Pravitz as the representative of intuitionistic propositional logic. But it also has, for me, and again, I know that for some people in this audience that's not the case, but for me, Biologia on this side here is also an important player, because what I want to have is triangles like that exist and work very well for intuitionistic propositional logic all over the place. That's what I've been calling the Curry-Howard, and I want to have this kind of triangle for different kinds of modal logics, different kinds of constructive modal logics, particularly the ones that other people have studied before, the ones that have been found to be useful in real life. And I've been doing that for a while. That's kind of again, as you guys may or may not have noticed that this talk was given to people who do not know of Curry-Howard and do not believe in Curry-Howard. So we kind of repeat it all a little bit, saying, okay, if you don't want to know much about Curry-Howard, just bear with me and remember that whenever I have two rules like that, I can decorate them with variables of type A, B, and stuff like that, and decorate them with terms like lambda x dot t or tu, and as I say, this works really very well for conjunction, for implication, which is what I wrote down there, and then for conjunction, and for disjunction, well, Girard would say that disjunction is the shame of natural deduction, but it works. It is there. We can do it. We can, if you don't mind having lots of commutative conversions, you are just fine. So my constructive modal logics will have operators box, diamond, which should be like for all and it exists, and hence not interdefinable, because we are being constructive here, right? And in constructive logic you don't have the existential is much stronger. We want to know how these two modalities should interact, given that they are not complete duals. And we assume that, well, I believe at least that the way that the two modalities should interact will depend on the expected behavior and the tools that you want and can accept. As I was saying, there's a proliferation of systems, and we are trying to choose the ones that are the minimum common denominator or the most acceptable ones, and it will depend on what you want to do with stuff and your applications, and especially the properties that you want to prove of the systems. And there is a collection of articles, lots of them, on why the proof theory of modal logic is difficult. And that's a kind of a good question, kind of, even this morning I was having my shower and thinking, why is that so? Why do I have to write, and every time I talk about that the proof theory of modal logic is difficult? But it's a fact that it is, and it's a fact that a poster child of the difficulty is S5, which, there is still debates on how to do it and what's the best way to do it and things like that. And one usual way to go about it is adding information to the syntax. So you can do things like hypersequence, you can do label deduction systems of different shapes and forms. And mostly that means that that you're adding some sort of semantics to the syntax. But as I say, there are many ways. There's lots of schools of constructive modal logic, and here are some, and I'm not going to go over them. And what I was kind of, since we started doing that in 2000, I started doing that in 2001, but people were doing that since 1999. People have been doing that since Fitch in 1948. Yeah, I think it's the first paper I know that talks about constructive modal logic. So people have been at it for a long, long time. I've been at it, and people from IMLA have been at it for not so long, but long enough, more than 15 years. And what happens here is that this goals that I was mentioning before, of having people talk to each other and use the same tools, or at least know about other people's tools, I don't think this goal has been attained at all. I think, and again, it's up to debate, and people, might disagree with me, but I think communities are still largely talking past each other. I think there's incremental work on intuitionistic modal logics, and some of the research program that I alluded to before is happening, but the work is very incremental, and in things like POPL, the conference, Principles of Programming Language, the guys prefer not to mention that they are doing logic. They talk about type systems as if they were completely unrelated to any kind of logic, and they chop and change, they choose and they mix and match to their heart's content without trying to think about what their type systems would mean if you're thinking of them as logic. And I think I've been very tired of the situation, so I do not know if it makes sense to try to change this. And that was the situation. And you might say, like Luis Carl said to me the other day, what is the point of saying that this is not working? I think the point of saying that it's not working is that, it should be possible to see where the problems are, what kind of is useful to have across communities, and what is not useful to have. And I think one of the reasons I'm so despondent about it is that I kind of thought in 1999, or 1992, whenever this thing started, we had I had lots of expectations. So I expected that by 2015 we would have fully worked out Curry Howard as a collection of intuitionistic modal logics. I thought we would have classical modal logic and intuitionistic modal logic completely mapped, and you would be able to see what would be necessary for what. And I thought we'd have a range of applications of both classical and intuitionistic modal type systems, and kind of worked out dualities and implementations in kind of both through search and normalization. And mostly we are not there yet. We are not there yet, and as I was saying, it doesn't even look like people are still working on this problem. I want to make sure that everyone is keeping track of the fact that when I talked about, some people, when they talked about modal logic or modal theorems or something like that, they do not think about the terms, so they think about just the logic naked without any terms, so bare logic. And some people think mostly about the terms, and then they can forget that there's a logic associated to that. And those guys are working side by side. They carry on. What is not working so well is actually putting the two together. And why did I think that the thing was going to be much easier? Well, because we had very, very big and early successes. And the successes were kind of the constructive for S4, which we had two different versions of it, one more dedicated to the type systems, one more dedicated to the logic. We had lax logic, which was something that, this is just a version according to my own work, so you guys don't have, it's not a good history. It's just saying that these are early successes that I was part of. But all around me and all around other people doing this stuff, there was lots of successes in particular systems. And This success is kind of vaguely stopped. So this is still the best behaved model system that I know of, and been used both in logic and in computing quite extensively. So Gödel and Girard used it to fairly good to do very good things in logic, and in category theory we actually using category theory we already knew what to do with it, because we as I was saying in the slide about Curry-Howard, we want to think about different proofs of the same theorem as being different morphisms in a category. So in this case, the category theory was already known, so meant that you kind of could simply grab off the shelf the work that the mathematicians had done before, and altogether it worked nicely. The axioms are traditional axioms. So you see the first axiom is the K axiom. Second one is kind of natural thing for necessity, in the sense of if A is known, then if A is proved, then A is true. The third one is introspection, right? If A is provable, then it's provable that A is provable. The fourth one, 1, 2, 3, 4, 5. The fifth one is just the dual of the if it's true, if it's provable, then it's true. So if it's true, then it's possible. And the fourth, well, axioms are not very deterministic. You can use different axiom systems, and you can have bigger axiom systems or smaller ones. So that's the one that I chose, but you could put lots of other things there. I chose this one because it already starts showing you that the diamond is actually parasitic somehow on the box, on this sort of on presentations that start from natural deduction. So the sequent calculus for this system existed much earlier. In 1957, Ojanishi and Matsumoto already had the system. Cut elimination works without problems, both for classical and intuitionistic basis. But the natural deduction was a little bit more complicated. That was what caused some issues. So the rule for the obvious rule that comes from the sequent calculus that we just saw, the second rule there, that in linear logic came to be known as promotion, this rule kind of caused all kinds of issues in natural deduction, because, and this is an important slide, but I do not know how we're doing in terms of time. No, I haven't kind of got where I want to get at all yet. But so this is kind of important, because whenever you're talking about different presentations of a logic, and you have axioms and natural deduction and sequent calculus, lots of times you say, oh, the problem with natural deduction is that sometimes we cannot get normalization. The problem with sequent calculus is sometimes you cannot get cut elimination. And you say, oh, that's an essential of life, we need to go for it. But the problem with this rule was not that it broke the cut elimination or the normalization. It broke before that. It broke the substitution. And the main reason I know for the diversification of approaches is actually trying to solve the problem here. So the problem here is that if you think about that rule, which says that if all, and the rule is very reasonable, right? If something is necessarily true, the box A on the bottom, it's necessarily true if all the assumptions that we kind of, if it's true, and all the assumptions it depends on are already necessary assumptions. They are all necessarily true. So, but so it's a very reasonable rule in terms of intuition of what necessity means. But it's a very bad rule in terms of how to compose things with it. So what happens is that the side condition that's not written there is this condition that, I mean, the condition is written in a funny shape because I'm saying that by that box gamma, I'm saying that all the assumptions inside that are boxed, right? So if the rule for the application, so if the side restriction for the application of the rule is that all the assumptions are boxed, then kind of composing with something totally trivial like any C proves a box A1 and C, so modus bonus getting a box A1, this box A1 is a good assumption for the rule, but the top of it is not. So when I pick up two totally trivial proofs and put them together, then I don't have a proof anymore. The application of the box rule to transform this B into a box B cannot be done. So the system is being broken before it actually started. And there are several different ways of correcting it. One of them is the one that I kind of did, that we did for linear logic with Bierman and Benton and Martin Hyland. And it's simply building in all the possible applications of things that would end up on your assumptions. So it's an ugly rule. And Pravitz uses a different thing. He uses a notion of essentially model subformula that Valeria de Paiva also used later on, notions of essentially model subformulas. So there's where the proliferations start happening. You kind of get different things that you think are more important. And so these are these original rules that I and then the guys did, but the variations are, so let me go to variations. The variation that is here is from the point of view of the terms, a much better variation. What we're doing here is that instead of thinking that the form, we are putting some extra information in the structure of the context. So we're saying that our context has things that might have a box on them and things that don't have a box on them. So I'm calling them X modals and X intuitionistics. And that rule here is exactly the same rule that I was saying is complicated, because over here I'm saying that to put a box on the A, what has to happen is that there was no thing, there was just an empty there. That's kind of, yeah, I'm sorry about the lack of pointer. So what happens here is that it's the same idea. You have a pointer? Oh, that's so kind. Thank you very much. Like this? No? The other way? See. Excellent. Yay. Lovely. Thank you. Red. Okay. So what I'm saying is that this rule here is exactly the same rule that we had before, because what it's saying, this is an empty thing. So it's saying that this is empty, so everything has to have at least one box in front of them, because those are the modal things. And these things that are intuitionistic, that don't have box in front of them, it has to be empty for me to add this box here. So this kind of has a collection of good properties for the terms. In particular, all the commuting conversions that were problematic before are dealt with here. So you have less impurity on the rules, less commuting conversions, but you have problems with your diamond, and you have problems with wanting a framework, wanting a collection of systems. And in particular, the model system that most real modal logicians want to deal with is system K. Oops. And here it's going to be a much more difficult one. You might say that the problem is that even the sequent rules are not as symmetric as they are for the constructive S4. If you remember, For constructive S4, we had introduction and elimination for box, introduction and elimination for diamond. Even if they are not totally pure, you had to kind of have diamonds inside of the boxes, you at least had a pair. For K, you do not have pairs. You only have a rule for box and a rule that has the diamond in this case. And even theorems kind of start being different. So here we do not, CS4 already did not satisfy distribution of possibility over disjunction, which the guys who are doing that from kind of more computer science point of view, dealing with concurrence, they wanted that. They didn't want this equivalence at all. They didn't mind this one, but this one they didn't want it. But if you are being a modal logician, well, you liked both of them. In particular, you like this one very much. So I hope at least you're seeing, and when I try to do that, because if you remember, we had two versions of this system, right? This version here, where I do not make any distinctions between the context, everything's put together, and I have a long and convoluted rule for introducing the box, and these ones are perfectly fine, but this and that are built lots of commuting conversions. And I had this one, which might look to you at kind of first time that this is the same, but much better behaved in terms of conversions. So it's much better for lambda calculus, but it is kind of odd in terms of separating the context into bits, and it's much odder in the sense that you cannot do it properly for CK. Oops. Okay. So I do not have, I cannot do that, red. I cannot do that. I cannot do the dual context sort of rules for the K only fragment. I can only do it for the box fragment. I cannot do it for the diamond. And I have script semantics and I have categorical models, but they are too unconstrained, and I have no ideas on how to go for a uniformity of systems. And so more work is necessary. And that's why I kind of said that that all my plans of conquering the world were kind of dashed. I cannot, we found stairs, can't move very much. And that's something that I actually wrote down for Professor Carnielli's volume, was when I was very much cross with life and everything, because that's how I felt things were. I wrote it in a fast script volume for him. But that was only me, and I'm just kind of, I'm sorry. It's I'm invited, so I'm talking about the things the way I was seeing them so far and stuff. And other people, including one thing here, was doing things in a very different way. Lots of people kind of thought about adding information to the systems, one of them being Alex Simpson. And he gets a very robust system for geometric theories, and he has natural deduction for a collection of intuitionistic modal logics. So his intuition is that what you need to think foremost about is the possible world semantics as interpreted in an intuitionistic meta theory. And then he can prove normalization for some of the cases and confluence for some of the cases. I put all the systems here, but it's not true. S4 was still recalcitrant. But on the other hand, systems are decidable and satisfy some finite model property, which is one of the other kind of points that we actually want to keep in place. And other people were doing slightly different things too. Arno Avron was doing hypersequence in 1996, based on older work of Pottinger and Mintz. Martini and Massini were doing 2-sequence. Dozen was doing higher order sequence again. Display calculus, Kratz and Rajiv Gorea were doing display calculus based on Belknap's old work. And Heinrich, as I say, kind of did a survey in 2002 telling how we could do these things with display calculus. And some other variations on sequence, multiple sequence, labeled sequence, nested sequence. So these things, this kind of line of work seemed to me to be more successful. In particular, very recently, 2013, Lutz Strasbourg and co-workers have been doing some nice work on that. So, you know, you have to start thinking to yourself, if the theorems that you want to prove are the right theorems for what you have. So, what did I want at that stage? I wanted constructive modal logics with axiom, sequence, and natural deduction formulations proved equivalent. I wanted sequence to satisfy cut elimination, finite model property, normalization for the natural deduction, confluence, and decidability for as many logics as you could have. I wanted algebraic, cryptic, and categorical semantics for all the systems around, and I wanted translations between these formulations that kind of showed us equivalences in embeddings. And I wanted a very broad view of constructive and of modality, but if possible with limitative results, meaning that that we could, by using this framework of translations between different systems and this framework of the desired results, we could decide which logics were not as good as the others, and you could say, okay, this is what these are the good ones. Let's kind of concentrate efforts on the good ones. Other people have slightly different desires for the systems. So Alex wanted that intuitionistic modal logic was conservative extension of intuitionistic propositional logic. So he wanted to have all the substitutions instances of terms of IPL and closed and modal correspondence. And of course, these two I also wanted. And he wanted to have disjunction property, and he wanted them to be independent like I wanted, but he wanted very strongly that adding the excluded middle to his intuitionistic modal logic systems went back to being the classical modal logic that we all know and love and which is unique. Or, I mean, there's a whole collection of them, but people don't talk about two different versions of S4 or anything like that. And Arnon wanted something similar too. You know, our desiderata were kind of overlapping, because he wanted a generic proof theoretical framework, should be able to handle a great diversity of logics. Yes, we want that too. Particularly want the ones that logicians have used already. Yes, I agree. We want it to be independent of any particular semantics. Well, that's what I was saying too, right? I was just saying that I wanted all the semantics for all of them. So independent of semantics is good. Structure should be built from formulas in the logic and not too complicated. Well, that's kind of difficult to decide, right? Complicated is a very subjective term, and should yield a real subformula property. Yeah, I know what he means. You know, you don't want a fake subformula property, but you know what exactly constitutes a real one is difficult. And wanted rules should be as standard as possible, and systems should give us a better understanding of the corresponding logics and the difference between them. So we all agree that this was good. But as I said to you before, we have problems. You know, things are going to be different for different systems. Some systems will satisfy this, and some won't. Thank you. And I mean, another quote from Arno that I think is very good. The framework of ordinary, and as you may not have noticed, Arno is very good at saying that he does not want to label the sequence with the semantics, because Simpson systems and Staranegri systems, and they all kind of labeled, they actually make the cryptic semantics part of the syntax. Arnold doesn't want that, so he says that there are logics with nice simple semantics and obvious interest for which no decent cut-free formulation seems to exist, when the cut-free system should seem not to exist if you do not have rules that use the semantics. So larger but still satisfactory frameworks should therefore be sought. We agree on that. And as I was saying, recent work from the guys, in particular Lutz, who is in Dale's lab in France, they kind of came up with an intuitionistic modal cube and a constructive modal cube, and so we have similar things. Now, is that good? Is that the end of the story? Well, not really. The syntax works, but the nested sequence are fairly complicated, and there's lots of properties that we still don't have. So, what's my summary so far? My summary is that constructive modal logics are interesting for programmers, logicians, and philosophers. Shame they don't talk to each other. At least two families of constructive modal logics have emerged from this work, one being CK and one being called IK, C for constructive, I for intuitionistic, and they have very different properties. It's hard to produce good proof theory for them. We have lots of augmentations of the systems, and so far what happens, as far as I can tell, is that the IK ones work better for model theory, that is the Simpson systems that are the same as the Staranegri systems, as far as I can tell, and CK works better for lambda calculus for having Curry-Howard. So I'm in a bit of a bind here because I'm kind of insisting on the categorical semantics, and maybe I have to drop this request. Maybe I can do the opposite. Maybe I can just go and say, well, maybe category theory can help more. Because another kind of very large amount of work that has happened in type systems recently has been the work on dependent type theory. And it is the case that in lots of mathematics, sometimes if you can make progress by asking more complicated questions, maybe we are thinking too small, thinking simply about the non-dependent modal logics. Maybe what we need to do is actually kind of put together dependency and modality, and that's what I mean by having a small system. So that's the second bit of my talk, the bit about a small system that's easy for some people, not easy for so many others, but where things work. And Shayla's telling me that I'm already over, so let's kind of go super quick over here. But, dependent type is a type that depends on a value, and it's an overlapping feature of type theory and type systems. And what they are used to normally is to encode quantifiers like for all and there exists. But in functional programming language like Agda, Idris, and Epigram, they prevent bugs by allowing very expressive types. And it seems that there is a renewed interest in notions of constructive modal type theory and linear type theory. So I hope that's the case. And I have a very simple system where you put together bits of old work. So you put together this old modal type theory with no dependent types that I was doing in 1998 with Neil Gunny and others. And you put together with that the work of Ika Ritter on calculus of constructions with categorical semantics but no modal types. And putting these two together, we get, well, as I was saying, it's easy for some, but it's a modal-dependent type theory which only works for boxes and boxes of style S4, and also needs for its categorical semantics fibrations. But then you have most of the type theoretical properties that you want: subject reduction, strong normalization, can add explicit substitutions. But as I say, only for S4 features, only for people who like vibrations. And it's just as well that we are out of time, almost, because these type systems are not pretty. I mean, this one is okay. It's the ICAOP 1998 one. We saw it early on, except that I didn't put the equality rules. I only put this rule that we discussed enough about the fact that here you have to have an empty set, and here you have a let that kind of binds the x1 to xn in the term u. Then it has all the properties. That's what the slide says. Everything that you want works for that. You have a basic dependent theory, type theory, with pi types and kind of traditional equations, and much more complicated because you have to build a context and you have to be careful with subject reduction, because subject reduction is a difficult one here. And you put the two together, and that's the new system. You put the two together, kind of doing very little, but it allows you to produce a box modality that is dependent, and it looks very much like a sigma type of some sort. What do I like about the system? I like, as usual, that it has all the properties that you want from it. The hard lifting is the work on modeling dependent types, which was done by Ritter and by Thomas Erhard, and it could have been done using Peter Dubier's categories of families. And it has this box modality, which is fairly different from the work of Penning et al., and also very different from a PhD thesis of Carsten Schack-Nielsen that I did not know about before. And I think the main difference is because at this stage in life, you need to decide if you want to do proof normalization or proof search. If you want to do proof normalization, which is what Schurman and Schack-Nielsen want, then their work will work for you, and it's similar to what we kind of discussed with Liano Cervesato a long time ago. But if you want to just do normalization, you get the category theory to work as a model. If you want to do proof search, you don't. And that's kind of the end, kind of the summary that we had before. I still think constructive modal logics are interesting for all the guys concerned, and that they should talk more to each other. I think the difference between models, different kinds of modal logics, and I'm not putting here the display calculus that Heinrich is kind of fond of, or because they don't, as far as I can see, the display logic kind of works for logicians, but not for people who can do proofs with this stuff. It's my impression, at least. And I think that some of the systems seem to be better for the model theory, so the cryptic semantics works perfectly fine, but some systems seem to be better for lambda calculus. You can make cryptic semantics here, but it looks ugly. And the same ways, you can't really do much in terms of, you can do lambda calculus here, but you can't do categorical semantics with this kind of system. At least I don't know how to do it. And I think I should do more comparison, because I need to show you exactly where their stuff doesn't work for the categorical semantics. I need to deal with diamonds, but no one else does either. And I don't know if I can extend it to the K, because what I'm doing here, as I said to you all several times, is S4, and S4 is better behaved. And I'm sure I can do it for linear logic, kind of dependent boxes model. But you see, I'm kind of building up fibrations. I have one fibration for the dependent types, and I have another fibration for the dependent box. And building up fibrations is complicated for everyone, especially for me. So that is where I stop, and I say thank you. Kind of ask questions, please.
We have about 5 minutes.
Yay! Please, Roy, what's up?
Are you using vibration just because that's kind of particularly what you're familiar with?
No, it's because I do not know how to do dependent types without vibrations. I mean,
There's again some sort of like
yeah, one could, but aren't they kind of essentially the same kind of? I mean, what is the? I don't know enough about that to tell you what are the differences. Like, for instance, I actually wrote to Peter de Beer to check if the categories of families would be the same, because one of my reviewers said this is no good. Why aren't you using the obvious normal model dependent type theory, which is Peter de Beer's? I said, well, I like Peter. No, it's fair enough if it. I mean, maybe it is the normal system. I don't know, but even if it is, I mean, I can do. Peter de Beer and I think that we can do the jumping from the vibrations that we have to categories of attributes of Cartmel and then to his. So you can do the translations and prove them that they behave. I hope. I have to confess that happens in May, and I haven't looked at it yet. But so I think it's a fair cop. I kind of I also had a model using vibrations for a modality, and that one you could explain much more, because of course the modality with simple type lambda on top of simple type lambda calculus, you don't need the vibration, but the vibrations have more elbow room. So in that case, the reason I needed the vibration was because I wanted to remove the modality. I wanted to. It's an old work on ILT and stuff. So the thing is, vibrations apparently have more elbow room. You can do things, and perhaps you can compose them and get bigger systems. It's all very much hopeful at the moment. It's not. I can't give you good evidence.
Okay,
my question will be less than a minute, but what will reply. So when you're talking about dealing with consistency, I understand that's not only technical, you're talking about also conceptual.
Consistency.
Okay.
Yes.
Now, when you talk about S4, or the system S-system, you mentioned provability against proof.
Yes.
Then when diamond, you said to be possible.
Yeah.
Why don't you, or you can have anything again, are you opinion about talking about this diamond there as really as consistency or admissibility? Is it okay for you, or is there anything technically against it?
I don't think that. I mean, I don't know anything technically against it. But what I'm saying is that I am thinking mostly formalistically on this. So I'm thinking that what determines S4 is those sequence rules that I had before, and hence the possibility that I have is the one that's given by those rules. I'm not thinking in terms of intuitive reasons for thinking of possibility. So for me, it's hard to think. So possible is what the sequence calculus are giving me already. And for this case, I have this problem that possibility seems to be much better modeled by things that have multiple conclusions. And then if I kind of try to make the move to the multiple conclusions that seem better behaved, just in terms of calculations, they seem much better behaved in the multiple conclusions case. But then I have all the other problems that multiple conclusions have. All this business that we discussed kind of years and years ago, the fact that when you break the things down, you have to see when the proof stays the same and stuff. So, eu sou entre a cruz e a caldeirinha, between the fire and the frying pan. That side gets easier, that side gets harder. But maybe that's what one should do, is kind of bite the bullet and go there and check. But the way that Frank Fanning, for instance, deals with the diamond is, to my mind, not ideal. Not. I mean, I think this multiplication of things, the multiplication of things can be seen as a good thing. And, lots of work for us, lots of ways of people using these type systems in programming and in different applications. But it can also be seen as a bad thing. It can show that we don't understand the phenomenon at hand properly. And in good days, I think A. In bad days, I feel that, we lost this game. No bad days, I'm the Dalek on the bottom on this. Sorry. I see.
Let's talk Let's approach it.
Thank you.